All right, we're going to discuss the details of the dynamic journal engine and kind of what makes it different from the standard conventional engine. Here we have a conventional piston rod bearing assembly out of a 250cc 4-cycle engine. Obviously, the piston fits onto the rod, and the bottom of the rod fits onto the crankshaft. It is basically a double articulating arrangement. As the crankshaft rotates around, the bearing in the piston allows it to move back and forth, and the bearing in the bottom, of course, lets it move through its stroke. In the dynamic journal engine, we replace this arrangement with a fixed piston, a fixed rod piston rod assembly, one piece, bearing in the bottom. The primary difference in the two engines is that the amount of force that is being applied to the crankshaft on a standard piston arrangement is fixed as by the stroke, by the
distance of travel,
by the offset. By the offset.
This came out of a 29cc 4-stroke weed eater engine, and its lever arm is essentially the distance from the center of the output shaft to the center of the throw journal on the crankshaft. This is a crankshaft. This is a camshaft. Okay, so you can see how much greater distance we have from here to here than you have with the crankshaft.
for the same piston.
For the same piston and the same displacement. That's the key. Piston goes down an inch in this engine, piston goes down an inch in this engine. So you have the same displacement. It's exactly identical. So any way you can increase the leverage without increasing the displacement, you're going to get better fuel economy. And it's essentially, we're getting anywhere from 2 to 3 times the fuel efficiency with the dynamic journal system over the conventional crankshaft. Yeah, we've gone through a whole series of bearings in the bottom of these pistons, and we've finally gotten up to one that's about 3 times the size as the original one. Okay, here's the original bearing, and we've gone through 2 or 3 in between this, and this is our final bearing right here, and it wears very well. We're not having a bearing issue anymore. All right, what we've got here, Kathy, is you can see from here up, they're identical. Okay. So weed eater engine, 4-stroke. It's important that it's 4-stroke because 2 strokes engines on the way out. You never get them past the
Speak up so we can hear.
What I'm going to do is I'm going to run them both for the exact same amount of time, 2 minutes each, and you can see the difference in the size of the prop. And you might say, well, this is a bigger prop, therefore it ought to get more power.
Mm-hmm.
Well, if you try to put this big prop on this stock engine, it doesn't have enough torque or twisting power to even run. It won't run at all. Okay? You can crank it, but it won't run.
Okay.
Now this engine actually cranks easier than the stock engine. We've almost got this one close. But the big thing is, this will demonstrate, what you'll see here when I run it, is you'll see this force gauge go over to about right in here. Okay? This engine, you'll see it go to about right there.
Gotcha.
About 2/3 of the power. Okay? This engine will be running at about 3,300 RPM. This one will be running at 1,800. Okay? So what does that tell you? Basically 2 to 1, right?
Mm-hmm.
Yet this one's putting out more horsepower. Okay? Now, the final thing I'll do is I'll take the gas caps off. I'll fill them both all the way up to overflowing. We'll run them for the same amount of time, and this one will take about 4 eyedroppers to refill, and this one will take about 8. So it's real easy to understand what's going on here. There's no little tricky levers under here. You'll see me fill the tanks up, and I'll run them with the stopwatch the exact same 2 minutes each.
Okay.
So with that, if you'll just stand over here.
All right, so now he's going to run it for 2 minutes on the time to run. big a Smith engine or something small as that. I did that on 452. I can take it apart in 6 minutes. I've done it. Right at 1800, about 4.5. With a minute and a half, 31 seconds. Degrees. I record that too. That's important.
That 2 minutes.
Vibrates more, going faster. Around 3,000. All right, so
Moment of truth. Drum roll, please.
2 minutes on each one.
2 minutes on each one. You'll be able to actually see the difference without the eyedropper, but we will do the eyedropper. Put a little bit more gas in there. Wait a minute, I'll do it. Okay, you see where that's at?
Mm-hmm.
All right, now look, can you see this over here? You see the difference?
Yes.
You can see that's down about ½ an inch, and this one's down about a quarter.
Yeah.
Now that's just 2 minutes, but you know, over 10 hours or something
Well,
like that.
exactly.
Okay, there's one. Two. Mr. Diesel would be proud. 3. It takes 33 of these to make 1 ounce. Let's build it right. We're going to hit right at 5.
Okay.
Okay, now, where you go with this? We should hit about 8, 9, or 10. gonna hit at 8. Yeah, maybe 8.5. Up 8. We'll call it 8. That was 8.5 in the overflow. All right, 5, 8. All engines, about 35% of the energy in that gallon of gas goes right out to the exhaust.
Gotcha.
35% just goes out to the exhaust. Both of these engines are doing the same thing. Okay? Though this one's running a little bit cooler, so a little bit less is going out to the exhaust. But the big difference is torque. How much twisting
Strength
power.
of the turning.
Take your, just go lightly on your wrist, and you can barely feel your hand. Now grip, squeeze hard, that's torque. Turn.
Gotcha.
You can actually feel the heat. Okay? So that's what makes horsepower is torque times the RPM. So if you got a lot of torque, if you got twice as much torque and half as much RPM, you end up with the same thing. Okay? We're getting even better than that because you're using much less fuel. Even if you didn't do the eyedropper thing, if you just looked at the RPM gauge and said, well, that one's turning 3,400, and this one's only turning 1,800, yet it's doing as much work or equal, you'd say, well, right off the bat, you don't even have to mess with an eyedropper.
Yeah.
You can tell.
It's using more
And
fuel.
then this one should last longer too, right? Here's what's in here. Okay. Here's the piston that I made.
So his invention are those two plates that are on the drive shaft.
The actual
Gotcha.
patent is not the piston. The patent is the
These two plates.
is these two plates, and they're cut in a mirror image. Okay, this exactly, when you put them together, that's called a mirror image. Everything on this, everything here corresponds to the same thing on there.
Okay.
Okay, so what happens is this drive pin follows that contour, that groove. You see it spinning
Yeah.
in there? Okay, so what that does is shaped like a cam in elliptical orbit. Here's your output shaft. Okay?
Okay.
Same as the output shaft on this crankshaft. This corresponds to that, and they do the same thing. But look at the difference. Look at the little tiny little lever arm here on a crankshaft engine, and look at the lever arm here. From here to the center of that is the lever arm.
Gotcha.
Center of this, center of that.
So the
It's
distance
greater.
of work.
Center of this,
It's
center of
approximately
that.
3 times as much.
Center of this, the center of that.
Gotcha.
Yet it
Center
only
of this,
it,
the center of that.
yet they drag the piston down a tube called the cylinder the same amount. It's a 1 inch. That piston goes up and down 1 inch each time. Even though this looks much bigger, it only pulls it down 1 inch. It goes
Okay.
from right here, that's top dead center, rotates around 90 degrees. Now it's pulled it down a half an inch. All right, rotates another 90 degrees, and it's pulled it down 1 inch. It's only pulled it down 1 inch, okay, in that 180 degree travel, okay?
Okay.
Right. So what we did after I saw Mike's presentation, just like you did, we got involved and we went to another South Carolina company down in Beaufort called 2SI, and they had been making some equipment for the Navy, I believe, right?
Marines.
Mike?
The generators for the Marines.
Generators for the Marines, and they were slow, and we had a project, and we said, would you build us a larger scale version? That's what we asked them. And Mike worked with them for a month or two, and we built that engine. And again, this is a, how many cc is this, Mike?
So this is 29.
29 cc, this is 250 cc, so it's substantially bigger. So we just kind of wanted to
We wanna
upscale
scale it
everything and sort of see what happens. So we built it, and then we said, well, we needed sort of a similar comparative test, but we didn't get quite that far down the road yet. But just for what we did though is we found a 250 cc Home Depot generator. So they're basically the exact same size engine, just like we're talking about with these. It has the same technology as far as the dynamic journal plates and all this stuff is in it. And we adapted the generator
Okay.
to this engine. So yeah, and I'm just going to show you really the difference is the RPM and the engine. When you listen to both of them, you'll be able to tell immediately that it is turning slower and yet it's still generating electricity at that slow speed. So I'll do this one, it's real quick and easy. 3,600 RPM to make the correct amount of hertz for your
To turn the
for like in
generator.
Europe, they use 50 hertz.
Okay.
In the US, they use 60. So that's just our standard frequency. This one, because the engine turns slow, we had to actually gear up the speed
Originally,
of the,
when he hooked it up, it wouldn't turn the generator
Fast
because
enough.
it was running too slow.
Gotcha.
So we put a gearbox in between the
sure.
two. You can see
Yeah.
the little
Right.
chain.
We just did a little gear step up right there to where we,
Oh, okay.
you know, it's basically a 2-to-1. So we're going to turn the engine 2,000 RPM, 1,800, and that will actually turn the generator at 36.
Okay.
To get it going as fast as the other one.
And I should have here. All the way down, barely idle. We're only 12 RPM now. We're still right at the end of it. So, you know, again, it's just to slow it down, but it's got the power. Yes, turn the generator, and yeah, we could hook a 50 hair dryer to whatever it's rated at.
Okay.
In other words, it doesn't matter. I'm just using the light bulb
He
as
just
an
wants to prove
example.
that it's really
But
making electricity.
it's actually making electricity, but you know, at that speed, it will do the exact. Well, actually, it'll do more work. You could probably put. You could put a larger capacity generator because the engine actually does make more power. You could probably, for this one, I think is rated at 3,500 watts. You may could put a 5,500 watt
Gotcha.
generator set, and again, and still, then you're using a third, you know, of the gasoline to get almost twice the power.
Yeah,
Right.
we put the engine we built in Dynamo, the company built it. They dynamometer tested to see how much horsepower, RPM, fuel consumption. Fuel consumption on this engine is 4.83. We'll just call it 5. 5 ounces per horsepower hour. That engine will use 12 to 14.
Research.
We believe the concept,
Those
Okay.
are all the engines and pistons that he's
but now it needs to go to
worked his way through over the years.
And I threw out a barrel of them.
to just
Each one of those takes 8 hours to fill.
But all we want to do, the initial idea was prove the concept,
Okay.
and we feel that we've
Yeah.
done that. So now, you know, where do we go from here? And that's kind of where we're at. And if it's the Department of Energy, if it's a university, if it's private industry, private interest, you know, we don't care. You know, we just would like to try to find some mechanism to
Take it
get
to the
us
next level.
from this to a production model.